Today I'm going to talk about shielding and image theory. It's an interesting topic because you need to understand this kind of shielding and image theory for many different applications, especially in the field called EMI and EMC. Stands for electromagnetic interference. Put an E. And the EMC stands for electromagnetic compatibility. Okay, and this happens for a number of reasons because the cell phone industry is driving this. You have about maybe 6 billion transistors in the cell phone, the expensive one. You have 6 billion transistors. In the cell phone. You can imagine how tightly packed the electronic components are. And you like to get them not to interfere with each other as much as possible. And sometimes this could be very difficult, so you have to resort to different kinds of clever engineering. And this field is very much driven by heuristics. Okay, so it's really difficult to do mathematical analysis, but we use heuristics and physical insight. To drive this field. Okay, let's see how we can understand this field heuristically. Let's take the example of 2 conductors. And if you have 2 conductors that they are placed somewhat like this, and that the conductors are oppositely charged. So they are positively charged on this side, whereas this other conductor is negatively charged on this side. Then the picture of the electric field will look something like this around this conductor. Okay, and I guess the figure is a little bit distorted. It looks a little bit better when it was printed out, but on this picture it's a little bit distorted. But what happens is that the electric field is 0 inside this conductor, and both of them are 0. And I'll explain to you why the electric field has to be 0. The reason is because if the electric field is not 0, say if it's not 0, if E is not 0, then J is equal to sigma E is not equal to 0. Then there will be current flowing inside this conductor. And that is not electrostatic shielding, because we want to talk about electrostatic shielding as to what happens in the static regime when nothing else is changing. The only possibility for this to happen is that E has to be 0. Otherwise, we have a contradiction. Okay, so E has to be 0 inside so that J is equal to 0. And also over this side, J is equal to 0. And then only would you have a quiescent state. Let me see if I know how to spell quiescent state. A quiescent state means nothing is changing. Okay, and that happens when the positive charges try to produce an electric field that is 0 inside, and then the negative charges try to produce an electric field that is 0 on the other object. And if the electric field is 0, that means that no current is flowing and you have reached the static regime Otherwise, you will never get to the static regime. If the current keeps flowing and flowing, the current will produce a magnetic field, the magnetic field will produce an electric field, and so on. So you will never be in the static regime if the electric field is not equal to 0. So the only possibility is for the charges to cancel the total electric field inside. Say if there's an electric field coming from the other conductor, it tries to penetrate into this conductor, then negative charges will pile up. Negative charges will pile up in such a way to make the E field equal to 0 here. And similarly, if this negative charges produces this electric field, positive charges will pile up on this end so as to produce 0 electric field inside. That is called electrostatic conductor shielding, and you can understand the physics quite well. So you don't need a perfect electric conductor, okay? So no PEC for electrostatic shielding. Just need the conductor. You just need the fact that sigma is larger than 0. That is good enough to produce shielding. However, this is for statics. And if the sources are time changing in state, like what we see here, if this is a dipole source, and this dipole source is a Hudson dipole, say, driven by some sources where you have currents flowing between the two spheres, then this electromagnetic field coming from this dipole is changing. And in this instance of time, when this is positively charged, this is negatively charged, then it has to be such that there will be negative charges on this side of the conductor. Okay, this is a conductor, this is a dipole. This is just a conductor. Okay, and then as the dipole is time varying, it will come to an instance where this is true, this will be negatively charged, the other one will be positively charged. Then what happens is that this part of the conductor will become positively charged. So you can only go from scenario 1 to scenario 2 if there is a current going back and forth. Okay, here the current might be flowing in this direction, and over here the current might be flowing in this direction. So a time varying electromagnetic source like a dipole, could be a Hertzian dipole, produces time varying electric field inside the conductor. So electric field is not 0 anymore. Electric field cannot be 0. However, you can show that the electric field has a penetration depth, very much like the skin depth. And we have earlier looked at the skin depth formula, that the penetration depth of an electromagnetic field into a conductor surface is proportional to this depth. There we did a very simple closed form example using plane wave. But this intuition still holds true, that the non-zero electromagnetic field will confine themselves to a very thin layer close to the surface of the object. Another thing to notice is that the charges are moving back and forth. So they have to have time to relax from one mode to the other mode. So the charges have to relax from this mode to the other mode. And there's a relaxation time involved. And this is very much similar to an RC tank circuit. Say, if I have a resistor and then I have a voltage source that is time varying. Okay, then the charges will go back and forth between the two sides of a parallel plate capacitor, and then there will be a time involved called the relaxation time. The relaxation time is the RC time constant. Okay, and it will take longer and longer for the charges to relax themselves if R is very large. And also, if C is very large, this relaxation time will also become bigger, and you can actually solve this problem in closed form. I'm sure that you have solved this problem before. Okay, and that you will find that the voltage in the current I is proportional to something like this. If you switch it off, if you were to switch the current off or the voltage source off, and if you have this, okay, you take the voltage source away, and then let some current flow in this circuit, and ask yourself, what time does it take? How long does it take before the charges go away? Because eventually the charges would disappear due to dissipation, and it goes away within this relaxation time. And also there is a relaxation time associated with a conductor, and that relaxation time is proportional to roughly epsilon over sigma inside the conductor. So it takes about this kind of time scale to relax from one mode to the other one. And you can see that this is very much like capacitors per unit volume. And then this is conductors per unit volume. So they have actually the same dimension. And if sigma is very, very large, okay, then this thing goes to zero when sigma goes to infinity, which means that if you have perfect conductors, perfect electric conductors, it takes no time for the charges to go from one mode to the other one. It takes zero time, which means that the conductors are very good conductors. It takes no time to move the charges back and forth around this thing, okay? So we come to an interesting demonstration of a Faraday cage. A Faraday cage is just a cage where you have wire meshes. You can actually make a cage out of chicken coop wires. And there could be very, very big holes on the side of the cage and on the top of the cage as well. And as long as you ground the cage, and you know that if you have a constant potential, if you have any surface where V is a constant, then the E field has to be zero inside. Okay, very much like this case over here. In the first example that we showed here, essentially if E becomes zero inside, then grad phi must be zero. Which means that phi is a constant inside the conductor, and then phi is also a constant inside this conductor. This means that inside the conductor at the electrostatic frequency, or in the electrostatic case, the potential is always a constant inside this conductor. And if you go and look at this case again, what you have then is that if this cage surface is kept to be equal potential, having a potential which is constant, then the potential must be the same, uniformly a constant inside, and there will be no electric field inside. So by such a very simple design, you can force the electric field to be zero inside this cage. And of course, this is close to electrostatic case. So, but however, if the electromagnetic field is slowly time varying, say if you have an electric field or electromagnetic field coming in, and if that electromagnetic field is slowly varying in time, it still very much would look like an electrostatic field. And hence you can see in this picture, this lady is well protected by this Faraday cage, even though this person is trying to attack her with a very high voltage source. The high voltage source cannot penetrate into this Faraday cage.